We have to cook an egg to cause a chemical reaction. The same is true for cookies. In other words, we have to apply heat. Without heat, we would still have a raw egg and raw cookie dough. Heat doesn't have to be there for every chemical reaction to start, but some kind of energy needs to get things going. Heat, light, and electricity can all kickstart chemical reactions. We refer to this as activation energy. Activation energy starts electrons hopping, but electrons hold the atoms of the molecule together, and they can't do that if they're moving to different atoms. So freeing the electrons means breaking the bonds between atoms. Doing so allows the electrons to form new bonds, and new bonds result in a new compound. Thus, activation energy enables a new product to form. Sometimes when atoms bind together, the bonds are very weak. For these bonds, not much energy is needed. The electrons start moving with very little help. For strong bonds, though, it takes a lot more activation energy to get things going. Ionic bonds. Atoms with only one electron in their outer layer are unstable. Unstable atoms trade electrons with each other to become stable. This is an ionic bond. Na is sodium. Cl is chlorine. Chemical reaction. Covalent bonds. Atoms can also bond by overlapping their outer shells. Then they share electrons rather than trade them. This is called a covalent bond. Two hydrogen, one oxygen, then they share their atoms. Reactivity, inhibitor, catalyst. Water must be present in the air for iron and oxygen to form rust. Rusty padlock. Catalysts can help to speed up a reaction. When a catalyst is added to a reactant, the energy increases. The higher energy in the reaction causes the molecules to work faster, producing the product much quicker. Catalyst. Catalyst bonds to reactants. Product is quickly released. Interesting inhibitors. Inhibitors slow and sometimes even stop chemical reactions. Catalyst. Inhibitor bonds to catalyst. Reactants are blocked when they try to bond to catalyst. Categorizing reactions. Chemical reactions fall into 6 main types: synthesis, decomposition, single displacement, double displacement, acid-base, and combustion. Synthesis. Pink plus a green is pink and green. The simplest type of reaction is synthesis. Here, 2 or more simple substances combine. When they do so, they form a more complex compound as a result. You can combine the elements copper and sulfur using synthesis. When you do, they will form copper sulfide. This compound is the product. Something to note happens here. Extra sulfur escapes as gas. When hot sulfur hits the air, it reacts with oxygen. A poisonous gas is created as a result. That poison isn't a product of synthesis, it's a byproduct. A byproduct is a secondary product. It's a product that is a result of a side reaction. Every reaction type can produce these kinds of byproducts. Luckily, not all of them are poisonous. Decomposition. A pink and a green to a pink, plus a green. The opposite of synthesis is decomposition. In these reactions, a complex substance breaks down into simpler ones. The reaction separates a substance. For instance, you can break down water into its elements. All it takes is a push from an electric current. The water compound will be split into hydrogen and oxygen. The electric current separates the liquid. That process is called electrolysis, but not all decompositions occurs in this way. Chlorophyll camouflage. Plants make food with a form of synthesis called photosynthesis. They use sun, water, and carbon dioxide to synthesize chlorophyll. Chlorophyll gives leaves their green color. When the days shorten and fall, plants make less food. Without chlorophyll present, we see the natural oranges and yellows of the leaves. Decomposition saves lives. Airbags in cars use decomposition to expand. They contain sodium azide pellets. When sodium azide is exposed to an electrical current, it decomposes to nitrogen gas and sodium. The nitrogen gas quickly expands and fills the airbag. Single displacement. Orange plus a pink and green goes to be an orange and a green plus a pink. Another type of reaction is single displacement. This is sometimes called a substitute reaction because one item takes the place of another. In these reactions, two substances compete to bond with another substance. For example, place an iron nail in a liquid solution of copper sulfate and watch what happens. The iron and copper compete to be part of the solution. The nail begins turning a pinkish brown color. That's because the copper is leaving the liquid compound. At the same time, the liquid turns from blue to pale green. The color change happens when the iron deposits where the copper was. Iron and copper sulfate become iron sulfate and copper. Double displacement, where an orange and green plus a pink and purple turn into an orange and purple plus a pink and green. In a double displacement reaction, there's an exchange of partners. Here, two new compounds form. This means there are two products. Let's look at an example. If two couples are dancing together and they switch partners, this represents a double displacement reaction. Margot and Tom are dance partners. Lucy and Andrew are a pair. As the dance progresses, a switch is made. During the switch, Margot and Andrew become partners, and Lucy and Tom become partners. This switch results in two new couples. Just like in double displacement, after the switch is made, new compounds are formed. Double the fun. You can amaze your friends and family with the help of a double displacement reaction. Just put baking soda into a container. Then add a little vinegar. Add food coloring for drama. Watch and enjoy the fizzy fun. pH scale. Acid-base reaction. The baking soda in our cookies represents the base part of an acid-base reaction. That's a special kind of double displacement. Atoms are usually neutral. They have as many electrons as they do protons. When an atom has extra or missing electrons, it becomes an ion. A substance with hydrogen ions is an acid. One with hydroxide ions is a base. Acids can be weak, like the citric acid that makes lemons tart, or they can be strong, like the stomach acid that digests our food. Bases also can be weak, like baking soda, or strong, like bleach. Bath soap is a weak base that results from combining a weak acid and a strong base. Shampoo is a weak acid that results from mixing a strong acid and a weak base. Hydrogen power. To measure the strength of bases and acids, we use the pH scale, where the pH stands for the power of hydrogen, as in hydrogen and hydroxide ions. This scale ranges from 0, strong acid, to 14, strong base. Neutral substances such as water would rank 7 on this scale. Which reaction is it? Is water a product? Yes or no? Well, yes, it's an acid base. No, Is oxygen a reactant and carbon dioxide a product? Yes, combustion. No. Are two or more chemicals combining to make one? Yes, synthesis. No. Is a large molecule breaking into smaller ones? Yes, decomposition. 2. No. Do any molecules have only one element? Yes, a single displacement. No, double displacement. World of chemistry. Chemistry doesn't just happen inside a lab, and it doesn't have to be boring. Chemical reactions happen all the time. They are all around us, even inside us. We can thank acid-base reactions for providing us with both our soap and our shampoo. Synthesis creates the water that washes them away, leaving us clean. Double displacement gives us those fluffy pancakes we get to eat for breakfast. When we're really lucky, that is. And decomposition allows us to turn that yummy breakfast into brain fuel. It's how we manage to stay alert all day at school. Enzymes in our mouths and stomachs act as catalysts. They help us quickly break down the food into energy. And good thing, too, because combustion engines makes our cars zoom. We need lots of energy as we make our way from home to school. Chemistry in the classroom can be just as exciting. After all, experiments are just another way to reveal the secrets of the substances that surround us. Observing physical and chemical properties in a lab prepares us to observe those same things in the real world, because the real world is a world full of chemistry. Baking with chemistry. Try baking bread at home without baking soda and see what happens. Leave different things out of the recipe for different results. Think like a scientist. How can you tell if a combustion causes a chemical reaction? Experiment and find out. What to get? 3 clear cups, hot water, powdered laundry detergent, purple cabbage, sealable bags, spoon, vinegar. What to do? Place 5 to 10 purple cabbage leaves into a sealable bag. Fill the bag halfway with hot water. Zip the bag tightly and squish the ingredients together until you have cabbage juice. Fill each cup halfway with the cabbage juice. Try to avoid pouring in big chunks of cabbage. Add a spoonful of vinegar into the first cup. Observe what happens and record the results. Add a spoonful of powdered laundry detergent to the second. Observe what happens and record the results. Add a spoonful of water to the third cup. Watch what happens and record the results. What kind of change resulted from each ingredient? How do you know? Your turn. Use all your senses. You can use all your senses to observe changes in foods. Have an adult help you look at and touch the food before and after it is cooked. Remember to wash your hands before and after touching it. Listen for changes while the food cooks. If it is safe, smell and taste the food before and after it is cooked. Experimenting in the kitchen may be the most enjoyable kind of science there is.